Hey Calculus, this is Mr. Ayton. This is going to be Unit 6 review, integration and the accumulation of change. I'm just going to go through the review exercises. There's a lot in this unit. This is one of the biggest units of study in AP Calculus, and so I'm going to get to it. It's going to be a little bit of a long one, but that's okay. Stick through it. Alright guys, here we go. The first thing is with Unit 6 is approximating Riemann sums, and if you remember there was left-handed, right-handed, midpoint, the actual area, there's trapezoidal rule, all those different things. So let's first take a look at the left edge. Remember the left edge, we're going to take this left point and we're taking the area of this box right here. Okay, and so that left point starts at 1, and what's the width of that box is 1/2. Plus, this next one, you plug 1/2 into your function, and we end up getting 5/4, and that is 1/2 in width, plus the next point, which is at 2, times 1/2 in width, plus the next point, which is at 13/4, and that's times 1/2. You add up all these sums and we get an area of about 3.750. You can try that on your own. It's correct, don't worry. And then for right-handed Riemann sums, we're taking the right-handed point. So obviously we're starting with 5, and he is going to be 1/2 unit. Plus, you can see right here, this next point is going to be this last point on the left-handed Riemann sums. That's 13/4 times 1/2. Plus the 2 times the 1/2, plus the 5/4 times the 1/2. You can see the difference between the left-handed Riemann sums and right-handed Riemann sums is this one starts at the left and doesn't have that last point. This one starts at the right, doesn't have that first point, and we end up getting 5.750. So you know the area is somewhere in between these. This left-handed, because our function is increasing, is going to be lower than the actual area, and since it's increasing, this right-handed is going to be greater than that actual area. So let's go to another type of Riemann sums, and this is midpoint. Midpoint's a little bit tougher, okay? And so you take the midpoint, which is 1/4, you would plug it in your original function, and you would end up getting 17/16. Okay, we multiply that by 1/2 because we're looking at 1/2. Then you take 3/4, you plug that in your function, you would get 25/16 times 1/2 plus a midpoint right here between 1 and 1.5. Plug that in your function, you get 41/16 times 1/2 width. And the last one, when you plug it in your function, gets 65/16, 1/2. And that one is giving you 4.625, and you can see that is coming much closer to the actual area. You can see the left-hand Riemann sums was 3.750, right-handed 5.750. Right in between is that midpoint. Trapezoidal rule is a really good way to do it. Remember, trapezoidal rule, we take this point right here, this point right here, we're taking the average or dividing that point by 2, and then multiplying it by that average, and then we're multiplying it by the width right there. Okay, and so that trapezoidal rule, when you would end up doing that, you would end up getting 4.750. You can try that on your own if you want. That's coming even closer to the actual area. How would we find the actual area? We would do an integration formula, and that integration formula would be from the limits of from 0 to 2 of the function x squared plus 1 with respect to x, and we would get 4.667. That is the actual area of my curve right there, under my curve. Okay. Sometimes they give you, they want you to find the area, approximating the area with left-handed, right-handed, trapezoidal, midpoint, and they give you a table of data. And so here we're going to take a look at the trapezoidal rule. Remember the trapezoidal rule? We're going to take this first point, this 0, this next point, this 72. We add those up and divide by 2. So you have 58 plus 72. 58 plus 72, divide by 2. Its width is 30. Plus, then you take the next 2 points, 72 and 62, and you divide by 2. Same thing, 72 plus 62, divide by 2. Multiply that by 30. And you're going to do this for 4 different values. You can try this out at home, and you end up getting 7852.5 for that area. Now, if we're using midpoint, remember what is midpoint doing is we're taking that middle point, which is a value between 0 and 30. The middle is 63, and he is multiplied by 30 because that's your width. The middle between the 30 and 60 point is 60 multiplied by 30, plus the middle between the 60 and 90 point is 69 times 30, and the middle between the 90 and 120 point is 74 times 30. They're all the width of 30, and that gives me the midpoint of 7980. Okay. Now, if I want to know the estimate average of that, remember, anytime I do an average, you're doing the 1 over the final x minus the initial x, that's your limits of integration, which ends up being 120, of my area. Okay, so that's 1/120th of 7852.5, and that gives me 65.4375. And what is that finding is, this is finding the average distance. You can see the problem says to estimate the area of a plot of land, a surveyor takes several measurements, and so that's giving you the average distance across the land. If we're using left endpoints, what are we going to do? And I'm going to start off with 0, and my left endpoint is 58, and I'm multiplying that by 30, right? Plus the next point is 72 times 30, plus so on and so forth. If I'm using the right endpoint, I'm starting off with 67 times 30, plus 61 times 30, plus ... And you can see if I'm using the left end point, and of course I'm still just sticking with four numbers, I'm going to get approximately about 7,800, 7785. This one, 7920. Okay, and that is if I'm given a table of data. Okay, so let's move on. We have our summation notation and definite integral. This is on the little bit more difficult side. Might be an equation you have to remember. This is when we take the integral from a to b of a function f of x with respect to x. The summation notation is the limit as n approaches infinity of the summation of from I equals 1 of delta x times f of xi. We have equations for each one of these things. So take a look here. I want to find out, for this one, I want to find out what delta xi is. Delta xi is b minus a. That's 6 minus 2 over n. That gives me 4 over n. And my xi is going to be equal to a. A starts at 2. Plus your delta x. What was our delta x? It was 4 over n times I. And so what happens is I put my delta x directly into my function. So you can see my function here is 1/5. 1/5. I'm going to put this 1/5 right here. 1/5. And my function is x squared. So this squared. And the delta x goes into that function. So 2 plus 4i over n. And what do we then multiply that by is your delta x, which is 4 over n. And so that would be your summation notation right there. If we take a look at another example of this, here we have cosine of x. And so I'm going to find first my delta x. How do I find my delta x? I got 2 pi minus pi over n. That ends up giving me pi over n. My xi is going to be my a, which starts at pi, plus my delta x, which is pi over n, times your I right there. Okay, and so what's my function? Is cosine of x. What do I plug in for that x? I'm going to plug in my xi, which is pi plus pi I over n. Okay, what am I going to multiply that by? Is pi over n. And that is my summation notation and how that works with a definite integral. Now we have all of our integration formulas. These are things that you want to know off the top of your head, all your integration formulas, and when you use them and use them and use them, you're going to end up knowing them and knowing them and knowing them. And so here I'm going to give you all your integration formulas. Obviously, if we integral a constant, that's going to be ax plus c. If we integral 5, that gives me 5x plus c. If it's pi x plus c. Don't forget your c. If I have a polynomial, what am I going to do? That x is going to be equal to n plus 1. We're going to raise it up, and what are we going to put in front of that is 1 over n plus 1, whatever that is. And so you can see that x cubed is going to be 1/4 x to the 4th. That 5 is going to be 5/3 x cubed minus the 8x squared. That square goes on your denominator. That gives you 4. Don't forget your plus c. Okay. If you have fractions, make it into 1 over x to the 4th power, make that x to the negative 4th power, and so that becomes x to the negative 3rd power, negative 1 over that 3 plus c, and that is your value. Now let's say we have an exponent, 5 to the x power. Well, that is going to be equal to a to the x power over 1 times natural log of that a. So you can see 1 over natural log of 5 times 5 to the x power plus c. If I give you an example here, that 2 ends up coming out front, and so we're 1 over 2 natural log of 3, and we have times 3 to the 2x plus c. Don't forget e to the x. What's your integration of e to the x is e to the x plus c. If it's e to the 2x, don't forget you have to think about the e to the 2x. You have to think about the canceling out your chain rule there of 1 over 2. So that is some of your integration. Don't forget, if we're going to do integral of sine of x, that's negative cosine of x plus c. Cosine of x is going to be sine of x plus c. Those are the two ones you have to know really, really, really well. So what's the integral of cosine of 2x? Obviously, that's going to be 1/2. Don't forget about the chain rule there. Sine of 2x plus c. You can use u substitution as well. Same thing here. Don't forget 1/6. And we have a negative because sine is negative cosine. Cosine of 6x plus c. One other thing is the integral of 1 over x. Don't forget what that is. That's natural log of the absolute value of x plus c. And so when we have this example right here, you can see the 3x squared, when we derive that, it cancels out that with that 3x squared. Just think of u substitution. Natural log of x cubed minus 5 plus c. Don't forget about here, we have natural log of cosine of x plus c, because what's the derivative of cosine of x? It's negative sine of x. That cancels out with that numerator right there. And this one right here, we have natural log of x to the 4th plus 1 plus c. That x to the 4th ends up being 4x cubed, so I need a 1/4 out front to cancel that chain rule out. Okay. Let's go to the fundamental theorem of calculus. This shows up all the time, is the fundamental theorem of calculus. We often call this the second fundamental theorem of calculus. I like to just call it the fundamental theorem of calculus. And so what do we know is we are going to simply plug in, this has to be a constant down here. We're going to plug in that x, and we're going to derive that x value, multiply it by the derivation. So here, the derivative of the integral of t cubed with respect to t from 0 to x, that x becomes x cubed, and then we multiply by the derivative of x, which is 1. So this next one, for example 2, you can see we're going from x squared to 0, and so the interesting thing is we can kind of flip that around by making that negative. And so we have from 0 to x squared, t cubed with respect to t. We're going to plug in that value right there, and we are going to end up getting x squared to the 3rd power, which is x to the 6th power. And I'm going to multiply by the derivation of that x squared, which is 2x. Don't forget the negative right there. And so we can simplify that just a little bit more, 2x to the negative 2x to the 7th power. This last one right here, we're going to plug in that x squared into the value right here. We're going to plug in the x squared, we're going to be plugging in this x squared to this t value right there. We get the square root of x to the 10th power plus 2. Don't forget, we have to do the derivation of this, which is 2x. Okay, and it's subtracting, then we plug in the x right there, and we get x to the 5th power, plus 2. That derivation of x is 1, and that is my answer for the fundamental theorem of calculus. Don't forget that derivation of those values. Okay, let's go to the first fundamental theorem of calculus. This is simply doing direct definite integration, and so what's my integral of x squared is going to be 1/3 x cubed from 2 to 0. I'm going to plug in 1/3 2 to the 3rd power minus 1/3 0 to the 3rd power. That's going to equal 0. 2 to the 3rd power is 8. I end up getting 8/3 for that. The next one, what's the integral of sine of x is negative cosine of x, and we're going to go from pi over 4 to all the way to pi. So we have negative cosine of pi minus negative cosine of pi over 4. What do I know negative cosine of pi is? Well, cosine of pi is -1, so that ends up becoming +1. Minus, what's cosine of pi over 4 is negative root 2 over 2. And so that ends up being 1 plus root 2 over 2 for that definite integral. That's first fundamental theorem of calculus. We have integration using U substitution. Let me go to my notes really quick. My notes are all over the place. There we go. We have U substitution right here. So what we always want to do with U substitution is we want to figure out what's the best thing to substitute. So this first example is we're going to substitute x squared plus 1. What's my derivation of that is 2x dx, which means 1 over 2 du equals x dx. You can see how that canceled out. And so we have 1 over 2. The integral of x dx becomes du. And we have square root of u. And so what can I do? I can finish that out. And that ends up becoming, that's u to the 1/2 power. So I have 1/2. That becomes u to the 3/2 power. I do the reciprocal of that, 2/3. Don't forget my plus c, and then I'm going to substitute back in. So I end up getting 1/3 x squared plus 1 to the 3/2 power plus c. Let's take a look at example 2. What are we going to use for our u substitution for example 2? We're going to use 2x cubed plus 5, which means my du is going to be 6x squared dx, which means 1/6 du is equal to x squared dx. That works in really nice. We have 1/6. We have our x squared dx, that's du. We have our u to the -4 power. That's a 4 right there, -4. That -4 goes up to become a -3 value, so we have 1/6 times -1/3 u to the -3 plus c, and then we're plugging back in our u value for that. We also, don't forget, some examples when you have some weird values where we're definitely going to use x plus 1 for our u, which means our du is going to be equal to our dx. That's nice. But see, we have an x in there. So we're going to have to rearrange this and say x is equal to u minus 1, which means this x is equal to u minus 1 times the square root of u, or u to the 1/2 power. And our du is equal to the dx. And you can see I can distribute now and have u to the 1st power times that 1/2 power. That gives you u to the 3/2 power minus u to the 1/2 power du. And now I can go and integrate, substitute back in u at the end. Okay. Another example, we have, what are we going to use for our u? We're going to use x squared. which means du is going to be 2x dx, and here we have 1/2 du is equal to x dx. We have our 1/2 of our integration, x dx is du. Cosine of u, what is the integral of cosine of u? Is going to be sine of u. So we have 1/2 sine of u plus c. We plug in the x squared again right there for the u. Last but not least on this problem, we have where we have our u and our du. Obviously, what's going to be used for our u is 2x cubed plus 1. What's our du going to be? That's 2x cubed. It's going to be 6x squared dx, which means you can see if I move a 1/3 over, 1/3 du is equal to 2x squared dx. And you can see I have 1/3 out front. I'm going, my 2x squared dx is equal to 1/3 du. And I have u to the 4th power. Now keep in mind, these limits of integration at the end, if it's a definite integral and you're using u substitution, you have to plug it in your u formula. So you can see u is equal to 2x cubed plus 1, which means when x is 0, if you plug in 0 in here, u ends up being 1. So the lower limit is actually 1. Then we're going to plug in 1. 2x cubed, 2 times 1 cubed, that's 2, plus 1, that's 3, so the upper limit is 3. And then you go and do your integration and you plug in these new u values. You have to switch everything from x to u when you're doing definite integrals with u substitution. Integration with long division and u substitution. Long division and u substitution. I'm going to try to find my notes real quick. I think I have it really quick. I do. I have it right here. So here we have a long division problem, okay? And so what we're going to do is we're going to divide this x squared plus 2 into the x squared minus 2x plus 4, and it would end up becoming 1 plus 2x minus 2 over x squared minus 2x plus 4. I can go and do my integration now, and that's with respect to x. The integral of 1 is x, and then I can use u substitution, and I find out natural log of x squared minus 2x plus 4. Don't forget plus c. And so that's where I had to do long division in there. You don't usually have to do long division, but sometimes it shows just kind of easy long division, which is something like this, where we have our x going into each value, so we end up getting x plus 3 minus 5x to the negative 1 power, and now it's a whole lot easier to do my integration. I get 1/2 x squared plus 3x minus 5 natural log of x plus c. Those are some special cases you see every now and again. You do have to know your inverse trig functions. And why do you have to know your inverse trig functions? They show up every now and then on multiple choice problems. And so you can see for the first one, this one where we have an a squared, we have minus x squared. This is going to be an arc sine x over a plus c. The next one does not have the square root. It's got a plus. That's 1 over a arctan x over a plus c. The last one is when we have an x out in front, and we have 1 over a arcsecant x over a plus c. And so you can see, what am I taking a look at here? I'm taking a look at the v is equal to the x right here. The a is equal to 3 because that is going to be 3 squared minus that x squared. So this is going to be an arc sine of x over 3 plus c. Here you can see the a is equal to 2. This v is equal to 3x. And so what are you doing? You're doing, this looks a whole lot like my arc sine. And so I have to do arc sine of 3 over x, 3x over 2 plus c. Don't forget, we have to do 1/3 because of that derivation of my 3x. according to the chain rule there. Okay. This next one, it's definitely looking like an arctan. You can see my v is equal to x, my a is equal to 4. And so what are we doing? We're doing 1/4 arctan of x over 4 plus c. This next one, same thing. We have a 3x, we have a 4, and so this obviously is going to be my 1/3, because of the 3x right there, times 1/4, that's 1/12, arctan of the 3x over 4 plus c. This last one right here is definitely the arcsecant, so I know it's an arcsecant. I have an x and I have a 5 right there, so I'm going to be 1/5 arcsecant of absolute value of x over 5 plus c. This last one here, we obviously have a 7x and a 5, and so we are going to be equal to, we have a 6 out front, okay, that's 6 on the numerator right there, so that's just a constant, it comes out front. So we have 6 over 5 because of the 1/5, and we have arcsecant of absolute value of 7x over 5 plus c right there. Boy, that was a lot. That was Unit 6. The biggest unit we will have is Unit 6. That is integration and accumulation of change. I hope this was a good review for AP Calculus AB. Have a good day, guys. I'll see you later. Bye.